Thank you, Anka. Thank you all for putting this on. I have to say, it's a tremendous thing, and I want to give some credit to Peter Abil, who actually started this whole thing about 4 years ago, and it's been going every year, and it's just it's tremendous to see it growing like this. And we're also happy to welcome our colleagues from all the other schools in the area. What I want to speak about in the next 10 minutes is some progress that we've been making with what we call the Dexterity Network. So this is all work that comes out of our lab. Many of my students are here today. We have some great collaborators, number of postdocs. And this is the issue I've been thinking about lately, which is e-commerce. So this has really taken off in the last couple of years. We now have an unprecedented amount of packages being delivered. I think Amazon's up to 500 per second. And the challenge is, how do you actually get these objects delivered? And if you look at the warehouse, for a typical Amazon warehouse, it's kind of like a hoarder's worst nightmare. They don't organize things nicely by category. They just throw everything into the next available slot, and then they have to have this challenge of somebody puts in an order for a box of Alka-Seltzer and a copy of Plato's Republic. And you have to somehow figure out where are these two things and put them together and get them out the door. Now this is challenging, and in a sense, right now it takes about a day or two. What they'd really like to do is get this down. And the faster they can make it, they believe, so if they can get it down to even a matter of hours, then the demand will go up. So this problem is going to just exaggerate over the next couple of years. And this is the particular area that I think we can make some progress in, which is the packing, the picking and the packing. And so this is non-trivial because, as I mentioned, all the parts, the scenario is constantly changing. So this is what's different than a traditional factory where you have one thing and you're doing it all day long. Here, you never do the same thing twice. So we have seen some very exciting developments in what I would call purely empirical methods that take an ab initio approach. They just essentially sample lots of grasps and then essentially do a form of reinforcement learning over time. And you're getting very interesting results. So, but the thing to notice here is the asymptote. So it seems that as we increase the numbers, the sample complexity is of a concern because we want to be able to get up to 90, 95, 99%, 99.9% for industry to accept this, to adopt it. Now, one thing that we all know is that we've had this huge success in computer vision as a result of ImageNet. And ImageNet was basically the collection of millions, tens of millions of labeled images. And that enabled basically, once you got to a critical mass, some scaling effects occurred, and we started basically being able to learn structure that was inherent to the images and be able to generalize beyond the training set. So I'm curious if we could do something like that for robotics. In other words, can we also generate a labeled data set? And for robotics, what we want is three-dimensional models, and we want the labels in these cases would be grasp configurations for these three-dimensional models. The nice thing is that we actually have now today, because of 3D printing, a proliferation of 3D models available. So I think this is achievable. And this is really the thought behind what we call a Dexterity Network. And I want to give full credit to Jeff Mahler. This is his PhD thesis. Now a number of other PhD students are involved in it. And so the first version of DexNet was in collaboration with Google. We basically set up a graphical model to characterize all the sources of uncertainty. And there's many because you can't sense things precisely, you can't control things precisely, and there's inherent uncertainty in the shape and properties like friction. So what we do is this. We take an object, say this red object here, and then we're going to consider many different grasps of that object. And for each grasp, we're going to consider perturbations. So we want to be robust. We're looking for grasps that are robust to these inherent uncertainties. And so what we're doing there is we're tweaking, moving the object. We're sampling from the distributions to be able to estimate and basically evaluate each of those different perturbed grasps. And that allows us to find grasps that are better than others. So you can see on the grasp on the right, as you can intuitively, it's more robust than the grasp on the left. So we can formalize that, and we basically do Monte Carlo integration. We're basically sampling from these distributions and trying to estimate a quality measure, which is the probability of success, the expected probability of success. And we essentially then want to optimize that. We want to find the grasp that that maximizes the probability of success. Now, there's some combinatorics to being able to pull this off, because you have to actually do this for every grasp on the object, and then with about 1,000 perturbations per grasp. And for maybe 10,000 objects in your data set, this becomes a fairly daunting computation. So some things we can do is we can make use of the cloud. So we're working with Google's cloud clusters. And we also do something where we can leverage some similarity. So once we've computed the solution for one object, or the estimates for one object, we can then transfer that to the other objects using multi-arm bandits, which has come up several times here today. We have to have a similarity measure, and this is where deep learning comes in, because we can use multi-view convolutional neural nets to be able to find similar objects for a new object that we encounter. And then we use a continuous correlated beta distribution to model the probability of grasp success, and we can then use as priors the success of similar objects. And we've been able to show, in fact, verify that this does work, and then we get scaling effects as we grow the size of the data set. So this is the idea. We want to grow this set, this fixarity network, and have them all these objects be linked by how similar they are. We're also very interested in adversarial objects. So we have been seeking adversarial objects, just as computer vision has been looking at adversarial images, and we're downloading these images and these objects and then 3D printing them for experiments. Now, we ran some experiments. They look like this, and here's the result. We got about 83% success. This is after we've trained this now. We've basically, using this technique, we've done all this stochastic optimization, and we get to about 83%. That's not very good, and it's because of uncertainty in the sensing and the control. So this is what we call DexNet 1.0. Now, here's the sort of block diagram of this system. Now, Jeff's idea was to remove two components, to go directly from point clouds to grasps. And this is a pretty big stretch. I actually have to say, I was not convinced this was going to work. But here's the idea. We're going to render point clouds synthetically with noise. And then as ground truth, we use DexNet 1.0 because we know what the probability of success is for those grasps. Then we have a very large data set of grasps that we can use. In this case, it's about 7 million grasp examples. And we feed that in to train a convolutional neural network here to estimate from a point cloud and a particular grasp what is the robustness of that grasp. And we use that to find robust grasps directly from point clouds. And this has been working much better. So we're getting up to 94% success. Again, not empirically learning, no, there's not reinforcement learning. It's doing directly from this analysis. Now, we've most recently been considering, now, up to there, everything was in objects in isolation. So during the spring, we started looking at objects in clutter, in bins, essentially. And now we do something, we take this idea a step further. We actually sample synthetic heaps of objects. So we use PyBullet to simulate dropping parts down. Then we generate the point clouds from those. We have, again, ground truth from DexNet 2.0, and we use that to come up with a training set for what we call DexNet 2.1. And here the success rate is 89%. So again, not where we want it to be, but it's showing some promise that we're able to routinely clear bins of 10 or 15 objects with this system. The nice thing about grasping, by the way, is that if you fail, you just get to retry, which is not necessarily the case in autonomous driving. So this is where we are. This is the plot. Now, the last thing I want to mention to you is what we're working on right now and I'm very excited about. And you'll hear there's a poster today. Matt Mattel is focusing on this, which is suction grasping. So many people in industry use suction cups. And so we want to apply the same methodology to suction grasping. And so we can, again, generate a graphical model. We can come up with a seal model, the seal of the suction cup. We can check if a suction cup seal will be, for a given target location, whether it's a good seal or not. We can also do a wrench space analysis based on the forces and torques. And then we can generate robust grasps, very analogous to what we did before. And we can then build this data set. We can do experiments. So we're getting 81% on the adversarial objects. But on the typical, on what we call basic objects down here on the lower right, we're getting 98% success. So we're very excited about this. And the next thing we're going to do is start looking at combinations or we're working with companies. We're looking at what we call composite policies, where we're putting together both suction and grasping. And that will be our work in the next few years, or the next few months. And then I have a number of other slides I'm not going to get to. So also want to do plugs for other students, but you can see their posters today. Thank you.
All right, so it's great to be here. Thanks to Anka and Marco for inviting me to present. So I'm going to talk a little bit about feedback control applied to legged robots. Basically, we are looking at the problem of walking over discrete terrain, so this is a safety critical control problem. Most of this work, all of this work is done by my students. I take the credit, I steal their credit. So just to give you some motivation, every single scenario that you see that cannot be navigated by wheeled robots, legged robots can navigate this. And people are motivated to work on legged robots because of this, but we don't have the control approaches to navigate these terrain. I'm going to show you one control approach towards this. So here's a kid. He's doing the stepping stone problem. Now, I'm not evil. The kid actually nails the stepping stone on the last step. What he fails to account for are the contact forces. So he fails and he slips and he falls. So if you want to design controllers, you not only have to take the constraints of the stepping stones, but you also have to take the friction constraints into account. So if you do things right, this is what you get. So I'm going to talk about the control approaches behind this. Okay, just to give you a quick background. So for legged locomotion, you have a set of flat outputs. You have a set of outputs that you want to drive to zeros. So you design a controller to drive Y to 0. One way to do this is to do input-output linearization. So you create an exact linear system using feedback linearization. And then you can do your favorite controller on this linear system. This could be as simple as PD. But once you realize that you can do PD, you can do something even more advanced. Now, thanks to Slotin's talk, I can now talk about control Lyapunov functions. So instead of doing a PD control, now you can express a control Lyapunov function and enforce this constraint using the controller. So V dot depends on the control input. If you do this, your outputs go down to 0 exponentially. And this can be expressed as a single quadratic program that's solved pointwise in time. And QPs are really quick to solve. Once you have a QP, you can incorporate constraints such as input constraints, torque constraints, friction constraints, and so on. So let's move to the safety critical problem. So you want to move your swing foot and land on this. You make a single mistake, your whole system fails. This is sort of autonomous driving without the lane markers and so on. So the key here is control barrier functions. And it's very similar to control Lyapunov functions. You want to enforce the constraint of B being always greater than 0. Instead of enforcing this constraint directly, you look at the time derivative of B, which depends on the control input, and you enforce this constraint. It's very similar to the CLF constraint. If you do this, now your state evolves in this green region, which indirectly satisfies B greater than 0. So you put this together, you have a single quadratic program that can enforce stability, safety, and other constraints. The foot placement constraint can also be enforced through barriers. So you can construct a barrier such that your swing foot is inside this big circle and outside this little circle to guarantee your end time constraint. Now here is a simulation. You have information of this terrain one step ahead. You don't have sufficient time to do planning on the fly. So your controller is moving your periodic orbit slightly so that you're guaranteed to have a foot contact on the next stepping stone. This is a simple model of Rabbit. It can be applied to more complex systems. This is Duris, 20 degrees of freedom. Here, not only the step length, but the step width also changes. You can also do step length and step height. This is a model of Atreus. So this is really complex terrain. So we have knowledge of the terrain only one step ahead, so you don't have the entire terrain. So you can do worst case where the step length and the step height changes, and all of these nice, interesting animations. But everything works in animation and simulations, but here's an experiment. So this is 8 years walking on cinder blocks where the step lengths are stochastically changing. Now some graduate student has measured all these stepping stones accurately and is giving that information to the controller one step ahead. But also the robot places its foot at some particular point, and so it has to do some dead reckoning based on onboard sensors to correct for this. So here's where you have step height and step length changes. So there was a recent video that came out from Boston Dynamics a couple of days ago. So if you've seen that, they're doing stepping stones. This is our first approach for walking on stepping stones. Now, if you want to use perception, this is what the robot sees. You cannot really see where you're stepping. You can only see a couple of steps ahead. So we're trying to put a camera on this. So some preliminary approaches towards this. Simple depth segmentation can get you walking on the stepping stones. But now we want to move away. We want to look at deep learning. Everybody looks at deep learning. I don't know why, so we're looking into it as well. Sorry, Peter. Sorry, Sergey. OK, so what we're looking here is, so we have a safety critical control. So we want to put in a perception from deep learning that also does safety critical perception. Now, the controller could enforce safety critical constraints, but if your perception gives you the wrong estimate, your controller will go for that wrong estimate, and your system will fail. So you have to have both safety critical control as well as perception. So towards this, we have some initial results. So we have a sampled image. So we take one image at the start of each step, and we use deep learning to estimate what is the input to the safety critical control. And you close the loop, and you can achieve walking with the safety critical perception. So we still haven't solved the entire problem, so we're looking into solutions to this. So we're also looking into the problem of where you have robustness to model uncertainty. So you want to do safety control with unknown models. Lots of math here. So we're trying to enforce this Lyapunov constraint. With model uncertainty, you have these unknown parameters. If you make an assumption that they're bounded, then you can do a max constraint. So this becomes a min-max constraint. And then you can achieve robust safety critical control where you have dynamically moving stepping stones. So this is sort of Indiana Jones walking the Temple of Doom, carrying something heavy. So we're doing some experiments towards this. So this is about 70 pounds added mass. The robot weighs about 140, so it's almost 50% extra mass that the controller doesn't know. This is only standing, so we still have to do a walking. So once you have all these controllers for legged locomotion, you can translate these to exoskeletons. Some preliminary results on simulation and experiments. I'm not supposed to show you a video, so it's just a snapshot. My lab also does some work on aerial manipulation. So the goal is to design controllers to follow desired trajectory for the load, not for the quadrotor. So think of a swarm of aerial robots. So you replace all of these balloons with swarms. How do you design controllers to track the load position? So we have a bunch of things. So let me quickly wrap up. So this is controllers on high dimensional systems. You have 12 degrees of under actuation. So most of your robots that you work on usually are actuated. So this is a high degree of under actuation. This can also handle a huge uncertainty where the quadrotor is inverted, the load is inverted, and your controller can still guarantee convergence to this desired trajectory. So to wrap up, so I've presented a little bit about robust agility and safety for legged locomotion. I've briefly hinted on the work that we do in aerial manipulation. So thanks for listening. Good to be part of this.
So our next speaker is David Camarillo from Stanford, talking about the interesting problem in surgical robotics.
Okay, thank you for the introduction, Marco. Last year at this meeting, I presented some of the work that we're doing in the surgical robotic space of the lung, looking at how we would do closed-loop control and navigation toward an automated robot inside the lung. The assumption that we've been using up to that point was essentially that we have full knowledge of where we are inside the lung, and I'm acknowledging that we don't, and that's a very challenging problem. So that's essentially what I'm going to show you today is some of the early work we've been doing on really this is mostly simulation work on how to localize within the lung using a camera essentially as feedback for your sensor, ultimately towards robotic automation. And to remind you of why we're working in the lung, the problem we're interested in, both in the US and around the world, the #1 cause of cancer-related death is lung cancer. And you won't be surprised to learn that that's because of smoking. And although that's a problem in the US, it's an even bigger problem in other parts of the world. So as an example, in China, they have many more times the number of smokers we have in the US. And so they have, I would argue, an impending crisis coming in the future as this starts to turn into disease. And they have another challenge, again, using China as an example, is the number of physicians per capita is less, and this is even worse in other countries. So how are they going to deal with these types of health problems? And what I argue, in order to export the best medical technology that we have for under-resourced settings, automation using robots might be a way to do that, so we don't need the expertise of a physician. So we aren't the first group to ask questions about how we can use a camera to localize where we are inside of the lung. This is a nice paper from a few years ago by Higgins et al. And this just tells you the general workflow. We're doing something similar here, so I thought I'd show this by way of background. The first step in the process for getting a diagnosis for lung cancer is you get a CT scan. So that's here in the upper left. And they notice that there might be a nodule somewhere, and you'd like to go in and take a biopsy of that nodule. So in this paper, what they did, and again, we have a similar workflow, is the first thing you do is you generate a 3D rendering of the branches inside of the lung. So that's the middle picture here on the top. Then what you can do is you can render what you might call a virtual bronchoscopy. So you can show this image here on the upper right that looks like what an actual bronchoscope camera might see once you are inside of the lungs. And now then when you're doing the actual procedure here in the lower left and the bronchoscope is introduced down into the lungs and you take a photograph on the lower right, the problem then is how do you align the real bronchoscopic image from the virtual rendered image from the CT? And if you can align those two, then you know where you are inside the lung. The advance that was made in this paper was that they were able to achieve a real-time registration, and that's important for being able to do this intraoperatively. The way that they did that is by not needing to render many of the virtual CT images in real time. That's computationally intensive. Instead, what they did is they warped the actual camera image. And so although that was certainly an advance, one of the challenges that they ran into is in terms of the accuracy. So if you want to navigate through the lung in that kind of little halo there, that's the first 3 branches roughly, so the lung continues to branch and branch. The diameter inside the airways is about 5 millimeters, okay? So if you want to do robotic control inside of that, you need your sensor, probably do better than 5 millimeters. And that was about the level that they achieved in this paper. Unfortunately, only about half of the cancers occur in those first 3 branches. So we would like to move much deeper into the lungs and get the other half of the cancers. And the branch diameters deeper into the lungs get down to about 2 or 3 millimeters. So our target is to be able to have a localization system that can have a couple millimeter accuracy so that we can do this autonomous control. So like everybody else in the audience, it looked like we've had to turn to deep learning, and I'm probably the least well-suited person to do this, but we've had no choice. And so the way that this works is as follows, pretty straightforward. There's 2 images that go into this convolutional neural net. The first image on the top here is what you see from your actual bronchoscope. The next image on the bottom is your rendered virtual bronchoscope images. And then as you feed it into the neural net, what you get out on the backside is a 6-degree of freedom transform between the 2 images, and that can help you do an alignment. Now we need to run this iteratively to achieve real-time registration, and so this is what it might look like at the first time step, and then as I tab forward to the next time step, what you would do is you would then register and adjust your virtual image to match your real image. As I go back and forth a couple of times here, you can see that after you do this registration, of course, your real image will then move again, and you continue to iteratively run this process. And the idea is it should keep you registered as you move along deeper and deeper into the lung. So how do we train this neural net? We can run a video of the simplest thing you can do is you can pick a centerline path. We want to use the virtual images that will tell you transformation between 2 different views. So if you run a centerline path, you can get a bunch of different views that would look like an actual bronchoscope path down the center. But of course, you don't know exactly what path the user might take. So we introduce, let's see, this is not it. Let's see if I can get to the next. There we go. So please don't get sick. This is, of course, sampling from a bunch of different positions and orientations along the path in order to explore potential images that you might see in the real bronchoscopy so that you can then take those image pairs and register it. at any given point within the lung, and we're stepping through this at about 500 microns. We're sampling every 500 microns along the length of the lung, and that is because we believe that will basically be a smaller resolution given the frame rate of the camera, about 30 hertz, so we'll be sampling sufficiently here. At each time point, we generate about 20 virtual images here, and then we try to introduce some noise to show the types of variability that you might see in an actual bronchoscopic image. These are 20 images from a single point in space, and essentially what we're doing here is we're changing the light intensity, we're changing the smoothing, we're also introducing obstruction. So one of the real challenges here, and again, this is just simulation data I'm showing you today, is that in real bronchoscopy, you might have a bubble that pops up in front of you, and you don't want that to trick your algorithm. And so, we introduce these little kind of pixelated squares here as a means of putting obstructions in. And so, again, this is just simulation that I'm showing you, and when we've done that training and we test on a simulated real, I guess, in quotes, camera image, what we see is that if you take camera images that are a varying distance apart, so that's what's here on the x-axis, if the distance between images is relatively small, about 3 millimeters or so, and given the speed at which the bronchoscope moves and the size of the airways, we would expect sequential images to not be further than 3 millimeters apart. These preliminary results show that we can get errors that are under 2 millimeters and would in fact allow us to explore the full lung. And again, as I said, this is just simulation. We are cheating to some extent because this is the distribution that we sampled from for our training. So, we were only training with a few millimeters of error between images. And of course, if we go to 4, 5, 6 millimeters between images, which we don't think is that likely, the error would be much higher. So we still, of course, have to prove this out in real images. And again, the idea is to use this as a feedback control mechanism, ultimately for automated surgery, and the neural net will now essentially serve as our sensor. And so out of the robot, a camera image will come back in. It will be compared with the virtual rendered CT. You'll get a transformation between the two, add that to your prior time step, and feed that into a motion controller so now that you can follow your desired trajectory. It appears that I am out of time, so what I'll do is I'll just let this video run of a simulation of closed-loop control, and also acknowledge my students who are the real learning experts here, Jake and David, who've done some excellent work on this project. Thank you very much.
Thank you, David. And our last talk for the morning is from Masayoshi Tomitsuka from Berkeley.
So I'll be talking about safe and efficient robot and human collaboration for next generation industrial co-robot. So this is for robot on the factory floor. And this research has been going on at least last 3-4 years. And it has been recently funded by NSF, but also quite a few of my students have been lucky to get Berkeley Fellowship and several industrial sponsors. I don't have a nice picture of the student, but I listed student to acknowledge their participation. Okay. So industrial co-robot factory automation, it has been talked many years that if we take robot out of cage and let robot interact with human, we can accomplish a lot of things, like taking advantage of the good part of the human and the good part of the robot. So take the best of the two worlds. But in doing that, there are several issues. At least two critical issues one is safety. You don't want to see that either robot or human be hurt. Okay, they shouldn't be colliding. And also being too cautious about if we drop the efficiency, that's not what we want. So that's also an important issue. And as a part of the research, to ensure those two things, robots should be able to recognize environment. There are lots of interesting things going on. And we are looking at the robot from stationary robot to mobile robot. And some of the examples of human-robot collaboration, our early work looked into read-through teaching and robot skill learning from human, learning by demonstration, or more recently learning by analogy, and also collaborative execution of tasks, emphasizing safety, efficiency, environmental recognition, and of course, real-time implementation. The first example, robot programming, the very traditional way of program robot is to use teach pendant. But this teach pendant, if you talk with factory people or industry people, it's a very time-consuming part. So you would like to be freed from this kind of robot programming because it takes long time, and if slide changes, you have to reprogram again. So that's, we started looking at read-through teaching. This has been also done in robotics industry for some years. It's a very intuitive method, but works well. So human worker grabs the robot and effector directly and guides the robot along either trajectory he wants or to the goal we want. And while doing that, let robot learn how it was done. Then if this similar situation happens, robot can do execute by itself. It's simple, but there are several, of course, problems, limitations. One is, of course, coming from safety. You cannot give too high bandwidth control to this type of loop. Essentially, in doing that, we are relying on the force feedback. But if the loop is too, the bandwidth is too large, it may not be so safe. Oops. How do I? There is a movie that I would like to learn. Okay, so for teaching this kind of things, the teaching pendant may take 28 minutes, but if the robot, the read-through teaching, it can be accomplished in a few seconds. And also, some of the mechanism we just designed to make it sure that robot become not wired by itself. Okay. Then the one limitation is because of limited bandwidth. If you have some insertion job, peg in the whole insertion, you cannot bring the robot or peg very parallel to the hole. So you can bring approximately, and from that point on, you have to really do some other operation. How do you align the peg and hole and so forth? And for this, we have also looked into some human way of doing. For example, what human does is to bring it parallel. What he does is he might be even he can close the eye, he can look for the hole, and once he comes close, he can make it parallel and do insertion. And in doing that, some key relationship is once the peg makes some 3-point contact, you can predict what is the force sensor output and the angle. And if we make use of that information and automate, the robot can do peg hole insertion based on that information. So by doing that, we achieve a very reasonable. Oops. Okay, so this is, again, a video showing both the read-through teaching part and peg hole insertion. You bring it, make 3-point contact, and then based on force sensor output, we make it link to the hole and peg aligned and do insertion. And of course, if you have new workpiece, you don't have to do the first part every time because robot has already learned. Now, more recently, by the way, the student in the movie was Tae-Tang, and more recently, he is looking at learning by analogy. And here, intent is when you teach, you try to minimize the number of things that you have to teach. And based on very limited set of knowledge, the robot can automate a variety of things. So this is, for example, one case that you have taught robot this type of basic patterns on the right, and based on that, if the desired shape is given, robot goes to some database and figure out how he can do to make a shape. It doesn't have to be a shape stored in the pattern, and in this particular case, most of the shape appears to be in the remembered memory, but and also rope may be placed very randomly at the beginning. So look, we can do this kind of thing. Also, looks like a little bit like what Ken was showing. Oops. We are trying to, for example, he's trying to say that we teach the shape, training shape number is minimized, and based on analogy, how that knowledge can be applied to the test object of similar things. And this is from some certain cases. This is through at the training part for this bench, flyer he learned, but once it learns, it can pick up similar looking object. And this is for some bottle, and he's teaching to grab some neck aspect, neck part, then it doesn't have to be exactly the same. Then finally, the human and robot sharing the workspace, this kind of scenario, we would like to have both safety and efficiency. So this is Chan Liu's work, and we have parallel the optimization path, one for addressing the efficiency, how we can do the efficient operation. This is more long-term planning. And then more looking into more current measurement information, we make it, okay, we make it safety, and that's a short-term optimization part. So parallel structure will accomplish both, and we do it in real time. So for doing this, we have to have a very nice, efficient, feasible optimization algorithm. And one algorithm Chan Liu came up is the convex feasible or convex optimization to the algorithm. Original problem is not necessarily convex, but it approximates a series of convex optimization, and it accomplishes. And this approach is very efficient compared to other approach. So this is CFS and other approaches. And this algorithm has been applied to this kind of typical situation. This is for really robot and human collaborating, and real-time optimization is going on. And this work, recently I've started getting funding from the NSF, and we have some for 3 packages that they are already, good part has been already addressed, T1, T2, T3 listed here. And for T1 part, environmental monitoring, I'm just showing one last video. Okay, this is huge, okay, looking into the interacting with robot. Robot knows what kind of the assembly operation she wants to do, so there is some flow, okay. And successful collaboration, okay. Thank you very much.
Thank you. So this concludes the first part of PARS. We're going to have a 1-hour break for lunch, and we are going to reconvene on time at 1:20. So see you in an hour.